this problem then to do with using the sine rule or the cosine rule. Let's just look at this one example. We've got triangle PQR. So I've no idea what this triangle PQR is going to look like, but I do know that side QR, so let's label this PQR. So if that's angle P, this is side P. If this is angle R, this is side R, and so on. We're given that QR is 36.5 millimeters, so that's this dimension here. We're given that PR is 26.6 millimeters, so it's this one. And we're given that angle Q is 36 degrees. Okay. Can't use Pythagoras because we don't know that none of these are right angles. We don't know the right angles, so we can't use Pythagoras. You're going to use either the sine rule or the cosine rule. Can you remember what the thing is? Exactly right. We use the sine rule because we've got one of the ratios. We know that side and we know the angle opposite it, so we can use the sine rule. Okay. What can we find using the sine rule? Angle P. Why is it angle P? Because the other bit of information means that we can make a ratio now. The ratio of that side to this angle is the same as the ratio of that side to that angle. That's what the sine rule says. So we can find angle P. Once we've got angle P, we can find angle Q, because the angles in a triangle add up to 180. Once we've got angle R, we can find side R. Okay? So I'm just going to give you a few minutes to work out what P, Q and R, what the missing angles are and the missing side is. So first step, sine P over 36.5. Write the ratio with the angle on top because we're after the angle, so write the ratio that way up. The ratio of the sine of P to 36.5 is the same as the ratio of sine 36 that we know over the side 26.6 that we know. So that would be my first step, to write that ratio down like that. The sine of the angle that I'm after, sine P, over the ratio of the side opposite, 36.5, is the same as the ratio of the sine of the angle I know, 36 degrees, divided by the side opposite that. That's the ratio that we write down. Then multiply both sides by 36.5, so sine P equals sine 36 over 26.6 times 36.5. Once you've found angle P, we'll stop at that point because you could carry on then and work out the rest. But we'll stop at that point. We could at this point say, therefore, angle P equals, remember using this inverse sine ratio, so the inverse sine will give you the angle of this. So we could try doing that in one hit on the calculator. P turns out to be 53.7 degrees. Yep. So there's one problem with this. We've got an angle of 53.7 degrees, and so we can then carry on. So if that's 53.7, we could work out what angle R is. However, there is another possible answer that we need to consider. We've not particularly talked about this, and we'll be looking at the wave function in more detail again, but the sine of an angle comes from the sine wave. And actually we'll be talking about this sort of thing in a minute when we look at angular motion. If I draw a sine wave, it looks a bit like this. Now if we consider where the sine wave comes from, if we consider something rotating, so if I have something over here and draw this rotating vector, so it's a bit like we were talking about last week when we got this force at a particular angle, and I think I mentioned in the example where we could have a rotating vector and we measure the displacement at a given time. So this rotating vector is rotating round in this way. So if I were to imagine it's along here and then rotating round like that, and at a particular instant in time, it could be here or here or here. It's rotating round. And what the sine tells me is the distance along the y-axis. It gives me the opposite side. If I complete the triangle at this point, look, then that distance here, the opposite, gives me the distance up the y-axis. And that's what the sine tells us. It tells us what the distance, displacement in the y direction is at any given point. So when the angle is 0, the sine is 0. In other words, the y direction is 0. As it rotates around here and gets to say here, say 40 degrees, this is telling me how far up the y-axis I've gone at 40 degrees. So if this was say 40 degrees here, that would be how far up the y-axis I've gone. It's gone a bit out of sync, so it's not quite there. And so on, assuming that the length of this is 1. So when I get to 90 degrees, this angle here is 1. So that will be 90 degrees down here. So if you type into your calculator the sine of 90 degrees, you should get 1. Because it's told you that at that particular point it's as far up the y-axis as it's going to go. It's reached this point here. Now, after 90 degrees, it comes back down again, and you can see that, in fact, there's more than one angle that's going to give us, say, if you look up the sine of 53.7 degrees, so if you key into your calculator the sine of 53.7 degrees, please. (0.87-ish). 0.81. So 0.81, that's 53.7 degrees. Are you focusing? 0.81 gives me 53.7 degrees. So if I go along to here and down, that would be 53.7 degrees. However, if I carry on to here, there is another angle that has the sine of 0.81. If you look at the symmetry of this wave, 53.7 degrees is here. Let me just rub these out because it's confusing the diagram a bit. That's 53.7 degrees. What would this be? How do we work it out? Yeah, if we look at this point here, that distance from there to there must be the same as the distance from there to there. I've not drawn it particularly well, but it should be. So if I take 53.7 away from 180 degrees, I'll have this angle here. What is 180 degrees minus 53.7? minus 53.7, somebody? 126.3. Key into your calculator sine of 126.3 degrees. You should get the same, 0.81. Okay, So there's a problem. In this triangle, and I'll look ahead to here, I've taken these out of the textbook because this is a problem in there. Look at these triangles. There's two possible answers. P could be 53.7 degrees, or P could be a slightly different angle, but a different angle. I'm not quite sure why that's not the same as that. Maybe we got a slightly different answer. 33, 50, no, that is right, isn't it? 50, 80, no, it's not quite, is it? It should be 126. Maybe this angle is not right. But anyway, the point is that we get two possibilities for P. And if you look at these triangles, P, the length P can still be 53.6 in both, 36.5 millimeters rather, and this length is still 29.6 in both, but this distance here, PQ, will be different in each case. It's as though this angle here could have come round like this and left. This is still 29.6 millimeters, but this line has come round to give us a different distance between P and Q. So beware when you're doing these problems with these triangles in particular that you could have two possibilities for the angles. Usually it's obvious which it is because you've got your triangle, you've got your structure, you know this angle is going to be smaller than 90 degrees, so that's the one we want. But if you have this sort of triangle and you end up with the answer 53.7 degrees, hopefully you'll recognize actually it can't possibly be that because it's greater than 90, so then you do what we were discussing, which was find out what the other angle is, the other value that sine could be. So that's something to be aware of, and that particular problem is looked at in the textbook, so you could try that out for yourself and see, have a look at the way they explain it. The point I wanted to make though is that there is more than one possible angle when you find the sine of something because of this sine wave.